All right. Just want to take a few minutes and use what we've learned in synthesis. So now there should be a way that you can make this molecule, metachlorophenol, from benzene as a starting material. And our pathway is going to have to explain how the two things are meta to each other. Of course, you couldn't just start with phenol and then do the chlorination reaction, because phenol, the OH, is an ortho-para director. So one of the ways that you can do this is first do the nitration reaction. I'm not going to write down those reagents because you know them, to put the nitro group on. Why am I going for the nitro group? Because I know that I can convert nitro to aniline, aniline to diazo, and diazo to phenol. But the nitro group is a meta director, so then I can do the chlorination conditions to install the chloro group on the meta carbon. And at that stage, then I can do first reduction to get the aniline, then diazotization to get the aryl diazonium, and then finally the nucleophilic aromatic substitution reaction to replace the diazonium with the OH. Just to be clear, here's the aniline, then here's the diazonium, and then that reaction does the nucleophilic aromatic substitution and replaces the nitrogen leaving group. Okay, you see that strategy there? That accounts for the meta relationship between the OH and the Cl. All right, how about this one? I would look at that and say, okay, I know how to make this bond via Friedel-Crafts alkylation. And then I would say, how do I make that bond? Well, the only way I know how to get the chloro on there, the iodo on there, is by reacting copper iodide with the aryl diazonium. That's the strategy, or rather the approach here, where we would first need to have the diazo leaving group, the diazonium leaving group, and then replace it with iodide. Let's just think about what order we should do things in. For some syntheses it matters, for others it might not. If we're going to use this strategy, this iodide used to be the diazonium group. What was it before then? Before diazonium, it's aniline. Before aniline, it's nitro. And the relationship between these two groups is para. Friedel-Crafts alkylation, so we probably don't want to have the nitro group on there first, because nitro is a meta director. Moreover, Friedel-Crafts alkylation doesn't work well on nitrobenzenes, or any benzene with an electron withdrawing group via resonance. So probably we want to do the Friedel-Crafts alkylation first, then we want to do the second part. So what would that look like? Probably the Friedel-Crafts alkylation to begin with, then nitration, and then once the nitro group is there, that same series diazotization, and then the nucleophilic aromatic substitution. Sorry, too fast. I skipped something, didn't I? You got to reduce, right? Reduce to the aniline first, then diazotize. Lovely new verb. And then nucleophilic aromatic substitution with copper iodide will get us to the desired product. Okay. Yeah, go ahead.
Wouldn't halide just be able to do orthopara as well, so you can take it all the way to the iodide and then...
Right. Could you take it all the way to the iodide first and then do the Friedel-Crafts? I think so. We don't have any examples. The only reason I'm somewhat skittish on that is we don't have any examples from chapter 20 of using the iodide and then doing electrophilic aromatic substitution on it, which means I don't know how good of an orthopara director it is. That doesn't mean it's wrong, and you're probably right. That's fine. Others? Yeah?
And the Friedel-Crafts alkylation doesn't work with aniline groups as well?
Right. You don't want the aniline on there first, although it doesn't work well with anilines for a different reason. Remember, the problem with anilines in Friedel-Crafts alkylation is actually that the aniline will intercept the catalyst, making a nitrogen aluminum bond, and if the catalyst isn't available to activate the chloro-leaving group, the reaction shuts down. Okay, so there's a fair number of ways. Go ahead, yeah. How long to get from benzene to the diazonium salt? That's a good question. I've not done this chemistry before myself, so I'm just going to guess here. But with any reaction that you run, the setup time and then the running time. The running time can be anywhere from 10 minutes to days. I'm not sure on this. I'm going to just say, let's say a couple of hours. We're just guessing at this point. Then you have to purify and isolate and purify your compound. At each stage where we have the possibility for ortho versus para, that's a purification isolation stage. If this reaction isn't 100%, then you have to isolate benzene from this. Techniques for isolating molecules from each other you'll learn about if you take the 353 organic lab or if you work in a research lab. It can involve distillation, where you're boiling things and condensing them at different temperatures, or it can involve something called chromatography. Both of those are somewhat time-consuming. Distillation's more time-consuming than chromatography. But purification could take anywhere from a couple hours to a little bit longer. So you're looking at probably multiple days to do it via this pathway. And chemists are always interested in methods that are faster and easier. So fortunately, we live in the world of chemistry. In this class, we live in the world of chemistry on paper, where if it looks like it's going to work, that's fine. Yeah. What else? All right, we could do a whole bunch of more practice problems on this, but I think it would mostly end up being just sort of a review of chapter 20. So I'll leave it to you to practice this kind of thing, but you'll need to get used to thinking of nitro to aniline to diazo to something else as a useful synthetic pathway. Lastly, I think, suppose we wanted to make, let's do a retrosynthesis where we want to make a diazo compound via this sort of diazonium coupling reaction. And let's just think briefly about how to go about this. Sure. Okay. So let's think about using just benzene as our starting material. So thinking about it this way makes it really easy to see all the bonds we have to make. Okay, I'm going to use a little red squiggly line. I can make this bond by electrophilic aromatic substitution chlorination. I know how to do that. I can make this bond via a Friedel-Crafts alkylation. That bond I can make in a couple of different ways. I could use this sort of diazotization strategy, or alternatively, I could use the azo coupling strategy. In other words, this bond could have been installed when I put the as the diazonium salt, and then this is the nucleophile I couple on, or this bond could have been installed as this molecule attacking a diazonium salt as a nucleophile. Same thing over here. I've got a couple of different choices. And then this one I know how to put on by the strategy of nitro to aniline to diazonium to nucleophilic aromatic substitution with OH minus. Okay. So you're sort of seeing how we can build up this kind of complexity. Let's think about where to start. Do you think it's a good strategy to make this structure first and then worry about putting the other groups on? Why is that bad? What's that? Well, so first of all, you're worried about whether this azo group is an ortho, para, or meta director, and I don't know. You would expect it to be, there's not information in your text, and I'm not really willing to speculate. There's a bigger problem than that. You're right to worry about regioselectivity, but there's a bigger, of like ortho, para, but there's a bigger problem than that at this stage. What is it? You can't add the CH3. Okay. Can you do the Friedel-Crafts alkylation after? One of the reasons, so if this were a deactivating group, and I'm not sure it is, that's what I'm struggling to speculate on. I only want the Friedel-Crafts to go on one side, right? And I got 2 benzene rings. So how are you going to control that? And the answer is you're not. So what I want to do is avoid those, I'm going to dodge those issues of which benzene ring gets modified by having everything in place on this one and then everything in place on this one when I bring them together. So the principle there is we're going to use what's called a late stage azo coupling reaction. we don't want to, we want all our ducks in a row by the time we bring the two pieces together. So if we think about that, then our first step backwards in the retrosynthesis is going to be one of two possibilities. We could use this as the nucleophile in the azo coupling reaction, which would leave this as the electrophile. And then, of course, the coupling reaction involves the benzene attacking the nitrogen here. We can see whether that's reasonable by seeing whether we can expect the azo group to end up on the para-carbon. And here we have an OH group that is an ortho para-director. So it seems reasonable that when we do the azo coupling reaction, the new carbon-nitrogen bond should happen with the para-carbon. Let's just briefly look at the other alternative. The other alternative would be to have the phenol side, or the left-hand portion of the molecule, be my electrophile. There's a C in there, you just can't see it. And then the right-hand side of my molecule would have to be this. And then we'd sort of have to look at whether that's reasonable as well. The methyl is an ortho para-director. The chloro is also an ortho para-director. The question is just whether they're going to prefer the same carbons or not. So methyl would prefer these. Chloro would similarly prefer those, though we will rule out the one that's in between the two because of sterics. So that looks like it would work too. We could definitely get that to happen. All right. So then we're down to two different synthetic pathways that look like they would work. We would need to make this and this through in our approach on the left-hand side, or we would need to make this electrophile and this nucleophile on the right-hand side. I think either one of these is probably okay. If I were going to pick, I think I would choose to use this as my nucleophile, simply because phenols, I happen to know the OH is an activating group. It makes things react faster than benzene, and so I like the idea of using this as a nucleophile, though I don't think the other method is bad. All right, I will sort of leave it to you to complete the synthesis. One of the troublesome features you're going to have to deal with is how do you get the methyl and the chloro meta to each other. That's actually not so hard, but I'll leave it to you to figure that out. I will write a note to myself to write the answer before I post these notes so you can check. All right, thus ends chapter 23. Sorry, 22. All right, chapter 23 I really geek out about. I'm sorry there's not that many of you here because it's pretty exciting to me. It's amino acids, peptides, and proteins, and I've been studying them for more than 20 years now, and it's an area of chemistry that I really like. Unfortunately, you know, we don't have enough time in one chapter for me to tell you all the things that are really cool about amino acids, peptides, and proteins. Where we will start today is with synthesis of peptides and proteins from amino acids. We'll talk about amino acids themselves at another time. So I want to describe something that's called peptide or protein synthesis. It's based on amide bond forming reactions. You've seen this before. This will be review from chapter whatever it was, I think 16 now at this point, in which we took a carboxylic acid and we took some amine, and we realized that we needed to do something other than just have the amine find the carboxylic acid. And the problem with the amine was that it's a base, and the problem with the carboxylic acid is that it's an acid. And so the first thing that's going to happen when an amino group sees a carboxylic acid group is the undesired acid-base reaction where you make the carboxylate and the ammonium. That reaction's favorable, right? The pKa of the ammonium is around 11. The pKa of the acid is around 4, 4.5, maybe 5. And so obviously the acid-base chemistry here is really easy to do. But our goal is to make not the ammonium carboxylate salt, but to make the amide bond. And so the way we did that in chapter 16 was we used DCC, and in most cases we use a non-nucleophilic base. And I showed you the mechanism for that previously. It was a mechanism you didn't necessarily need to memorize, but the idea is we convert the OH into something that's a good leaving group. And then the nitrogen of the amine attacks the carbonyl carbon, and we just do conventional nucleophilic acyl substitution chemistry in which the leaving group leaves. I guess we'll continue to use red for arrows, and then we need, again, the non-nucleophilic base to remove a proton from the nitrogen. Some people will show that proton transfer happening before the leaving group kicks off. Others will show it happening after the leaving group kicks off. Before versus after doesn't really matter. Okay, so that's amide bond forming chemistry. That should be a review. The complication, of course, is if you want to make amide bonds using amino acids. And I'm going to give you the simplest alpha amino acid that there is. This is called glycine. The problem, of course, is that this molecule has its own competing amino group. So that if I tried to use DCC and triethylamine to do a reaction between glycine and then some other amine, I've got a competition between potential products, right? I could make the desired compound, but then the amine on glycine might compete with the amine on here, and I might actually end up making an amide bond not with the amino nitrogen, but with a glycine nitrogen. In other words, I've got two different possibilities. And it gets worse than that. I haven't even shown you, but this glycine now dimer, where we made one amide bond, still has a carboxylic acid on it, which could get activated by DCC, and it's still got an amino group on it, which could react with that activated carboxylic acid. So you can see the potential not only for addition of another glycine on there, but now also intramolecular reactions. Imagine if this was a leaving group and this nitrogen attacked it, you could start making rings. It's kind of uncontrolled, right? So we need a way to prevent undesired side reactions. And the strategy for dealing with this is going to be using protecting groups. And the goal here is to avoid undesired amide bond formation. So there are a lot of different ways that you might envision this protecting group strategy working. But the way that's really been adopted by chemists has been to do something to the amino group on your amino acid that prevents it from being a nucleophile. Now remember, the classic things that define a protecting group is it has to shut down the undesired reactivity. In other words, here the protecting group has to stop the amino group from the amino acid from being a nucleophile. Second, it has to go on easy. That means high yield and fast. Those are two separate things, 100% yield and really fast. And then it also needs to be easy off. Again, high yield, fast, and ideally no purification. That would be great, is if you could either the putting the protecting group on or removing it, both were high yielding, fast, and no purification. I will say that the putting the group on is called a protection reaction. Removing the group is called deprotection. And a huge amount of every synthetic chemist's efforts to make molecules involve putting protecting groups on and removing protecting groups. And in particular, if you can get reactions to go the way you want without protecting groups, that's really awesome chemistry. So let me show you some strategies that are used for avoiding undesired amide bond formation. And again, I told you we have two problematic groups with the amino acids. You've got the amine and you've got the carboxylic acid group. And so let's show you what some protecting groups are for amines. These have fun abbreviations, and they're fun because you don't really want to know what they stand for. The Bach protecting group is the following. So what I'm drawing for you here is a Bach protected amino acid. This is Bach protected glycine. Sometimes people will not draw out the structure of the protecting group. They will simply write the abbreviation on the protected atom. Of course, you've seen this before in our silyl ether protecting groups. Do you remember the TBDMS groups? Yeah. So we're doing a similar sort of thing here. This type of protecting group is called a carbamate. And the nitrogen is no longer a good nucleophile. The reason it's no longer a good nucleophile is that it is tied up in resonance with this carbonyl group. And that, you could imagine that carbonyl group being somewhat electron poor because it's got an electronegative oxygen attached to it. In any case, this is like, the carbamate is like an amide bond, and the nitrogen is no longer a nucleophile because, a good nucleophile, because it is involved in resonance with the adjacent carbonyl group. However, the carbamate is different from an amide bond because it is easier to break than the amide bond. So let's first talk about how the Bach group is removed, because it's only if it's removable that it's useful to us. Then we'll talk about how to put it on there in the first place. Oh, sorry. Bach stands for tert-butyl. That's the tert-butyl group. B is for tert-butyl. Some people, it used to be called T-Bach until people just dropped the T. You can call it T-Bach, but people will look at you funny because nobody calls it that. The B stands for tert-butyl, the O stands for oxygen or oxy, and then the C stands for carbonyl. Tert-butyl, oxy, carbonyl, Bach. And it's kind of cute how if it's, when the letters are read from left to right, it does actually tell you what the structure should be. The Bach group is easily removable under acidic conditions. So removable with a strong acid. And what's thought to happen is that the reaction is something of an SN1 reaction in strong acid. I'm going to show the reaction, sort of all the deprotection reaction or removal, all at once, though you could show it stepwise. Here is your strong acid. We're going to show the nitrogen getting protonated. At the same time, we're going to show the electrons in this carbon-oxygen bond leaving, this is the sort of SN1-like step, leaving with the oxygen. At the same time, we'll show those electrons kicking down to form CO2. I'll highlight where CO2 is embedded here. And then the electrons in the bond between the carbonyl carbon and the nitrogen just go on to the nitrogen as a lone pair. After this reaction, you have a tert-butyl cation, which is unstable. You have CO2, which bubbles off as a gas and is very stable. And then you have your liberated amino group. Usually at this stage, you're using strong acid and you need some weak nucleophile like water present. And water or some other nucleophile intercepts the T-butyl carbocation to make ultimately tert-butanol. And so the reaction proceeds very quickly. Kinetics here are really fast. Bach deprotection is super fast. In part, it's driven by entropy because you lose CO2. The only other byproduct besides CO2, which goes away into the air, other than your amino acid, is tert-butanol, and that's easily separable from your amino acid. So this is a reaction that's fast, it's high yielding, and it doesn't require any subsequent purification. And it works because you've got something here on the other side of that oxygen that's potentially, we'll put in quotes, happy. It's not really happy, but happy as a carbocation. That allows the leaving group to leave. That allows the CO2 to do a decarboxylation, and the electrons that are left behind are picked up by a proton from acid, and that gives you your amino acid. So that's the deprotection reaction. Let's talk about the protection reaction. This one is also really easy. So here's an amino group. The strategy for protection is to use a reagent that's called Bock anhydride. This is like an anhydride that you've seen before from chapter 16, only instead of R groups on either side, you're going to have the tert-butyl oxy groups from Bock. And this is basically going to do nucleophilic acyl substitution. You can think of all of this as a leaving group. Usually you need some amount of a non-nucleophilic base like triethylamine. Nitrogen is going to be your nucleophile. Nitrogen's more nucleophilic than the oxygens of the carboxylic acid. Nitrogen is going to attack the carbonyl carbon to give a tetrahedral intermediate. There'll be some proton transfer and the leaving group leaves. And then what you're left with is your amino acid. Now Bock protected, but I'll draw out the structure. And then the thing that's the leaving group is this, which can also lose CO2, which pushes this reaction forward as well. You get tert-butoxide, which is going to pick up a proton, probably from one of the proton transfer steps in the nucleophilic acyl substitution. All right, so this is the Bock protection reaction. It is also high yielding and quick to do. Sometimes purification is necessary after the protection reaction, but that's the strategy, okay? So this allows you now to put a protecting group on the nitrogen and then to remove it at a later stage when it's no longer necessary. So far, what I've told you may be confusing because I just said how to take the Bock group off and then how to put it back on. Of course, we don't want to do that just for our own purposes, on, off, that's silly. But I needed to show you the on and the off reaction so that we can use them in context. Before we can do that though, I need to show you a protection reaction for a carboxylic acid. Questions so far though about protection? Okay. There are a lot of good protecting groups for carboxylic acids. I'm just going to show you one. There may be others. For carboxylic acids, there's tons of others, and I'll show you one. The classic protecting group for a carboxylic acid is an ester, because you can ester synthesis is pretty easy. Ester hydrolysis is also easy. If you are creative, if you are creative, you can use esters that are easy to hydrolyze even not under acidic conditions. All right, so so here's an example of an ester. The ester is a good protecting group because it lacks the acidic proton. And in particular, if OR minus is not a good leaving group, it is not really reactive to nucleophilic acyl substitution. We don't want, when the protecting group is on, we don't want the carbonyl carbon to be an electrophile. A decent choice for an ester protecting group for a carboxylic acid is what's called a benzyl ester. You can form the benzyl ester in a couple of different ways. You can do acid catalyzed ester formation. This is just the Fischer esterification reaction that you learned. And this protecting group is sometimes abbreviated as OBN, where BN stands for benzyl. If you don't want to do the acid catalyzed sort of Fischer esterification that we learned in chapter 16, you can actually do an SN2 reaction with the carboxylate as a nucleophile. So if you use benzyl bromide, where the Br minus is a leaving group, you can use the carboxylate, deprotonate, use it as a nucleophile. You probably need a non-nucleophilic base here. Deprotonate the carboxylate, use it as a nucleophile to do an SN2 reaction with benzyl bromide, and that will get you the benzyl protecting group. Importantly, as I said, we lack the acidic proton, and the carbonyl carbon is not really that electrophilic because OR minus is not that great of a leaving group. Okay, so that's the easy on. Let's talk about deprotection for the benzyl ester protecting group. Of course, there are a lot of ways you can think of to remove esters. You could do base catalyze, you could do base induced saponification. You could add OH minus, and that would attack the carbonyl carbon, and then the leaving group would leave. That's ester saponification, which we've talked about before. Ideally, though, as I said, for protecting groups, easy on, easy off. If we can, we want to use mild conditions. And in particular, if we're going to have multiple kinds of protecting groups, we want to be able to remove one without messing with the other. So the protecting groups we choose to use, we want them to be what I'm going to call orthogonal, which means we want to use conditions for the carboxylic acid deprotection that aren't going to affect the amino group protection scheme. We don't want to mess with Bach while we're deprotecting the carboxylic acid. So another strategy you could use for ester removal is acid catalyzed hydrolysis. That's a bad choice here, though, because acid conditions remove the Bach group. So we want something that's not going to touch Bach. The strongly basic conditions, it's not clear at this point why we're avoiding them, Bach doesn't come off under basic conditions, but there are other things that can happen when you use a strong base. It turns out that our old friend hydrogen and palladium on carbon does a beautiful what's called hydrogenalysis reaction, in which we basically add hydrogen across this sigma bond between the oxygen and the carbon. We reduce that sigma bond. I'll show you what the products are so you can see where the reduction is. We make benzyl alcohol. We had 2 hydrogens from H2 and 1 pair of electrons. Here are the 2 hydrogens from H2. I'm not sure which pair of electrons goes where, but 1 pair of electrons is from the original oxygen-carbon bond, and the other pair of electrons is from the hydrogen-hydrogen bond. So that's called hydrogenolysis. It's catalytic. It uses just hydrogen, and the benzyl alcohol is easily separated from the amino acid. And so this reaction is really quite easy to do. So now we've got ways to protect an amino group and to protect a carboxylic acid. Easy on, easy off. Go ahead.
Where does that second oxygen come from on the benzyl group?
Oh, you were so right, and thank you for catching that. I must be feeling in a better mood today because I did not attempt to insult you when you corrected my error. Still feeling bad. Sam, was that you last time? I think you lost a carbon. I'm sorry about that. Yes, you're right. So we reduce, the other oxygen doesn't come from anywhere. I'm sorry about that. We reduce the oxygen-carbon bond. We make actually not benzyl alcohol, but toluene, which is even easier to separate. Yeah, thank you for that. Good. All right, so let's show you how you would use this in a synthesis of a molecule where we're just wanting to make 1 amide bond between 2 specific amino acids. All right, so suppose your goal, don't know why you've chosen to do this with your time, but it's your life, not mine. You want to make the following, what we're going to call a dipeptide, and it's composed of 2 amino acids. This portion happens to be called leucine, and this portion happens to be called alanine. And you want to make it from the starting amino acids. This is L-leucine, where the L refers to the configuration of this stereocenter here. I'm just going to drop the L and call it leucine. If I meant the other one, I would say D-leucine. And then the second amino acid is this one, and this is called alanine. And notice that I want to make the leucine-alanine dipeptide. I don't want to make this isomer where the alanine comes first. Probably because I'm opposed to alphabetical order or something, I don't know. And this highlights a point that's important for peptides, and that is they have directionality. How do those 2 differ from each other? It's subtle. Notice that in the molecule that I want, my target molecule, alanine side chain, which is a methyl group, is adjacent to a carboxylic acid, whereas in the undesired alanine side chain, the methyl group is adjacent to an amine. Similarly, in the target molecule leucine's side chain, this hydrocarbon is adjacent to the amino group. Here, leucine's adjacent to the carboxylic acid. And this is actually one of the first things you need to know about peptides is they have directionality, they have different ends, they are linear polymers. This is called the amino, this side on the left is called the amino terminus or the amino end. And this is called the carboxy terminus or the carboxylic acid end of the molecule. Often people will just say N terminus. N is for amino group, and they will say C terminus. Terminus is how you say end singular if you're talking about multiple ends, the C and N termini. But if you mean just one of them, don't say the N termini because that irritates me. And I'm allowed to have pet peeves because it's my class. Someday when you're teaching this class, if you want people to say N termini, you can. But notice the difference in these two peptides. The N-terminal amino acid in this dipeptide is leucine, and the C-terminal amino acid is alanine. Here it's the other way around. Those are different. We're going to control which one you get based on our use of protecting groups. All right, so if I were going to do this, and I wanted, the bond I want to make is this bond between the nitrogen of alanine and the carbonyl carbon of leucine, then probably I want my starting material for that step to have leucine with its amino group Bach protected, so that the only thing that can happen to leucine is reaction with the carboxylic acid. And then I want to use alanine with the carboxylic acid group benzyl ester protected, so that the only thing that can happen to alanine is use of the amino group as a nucleophile. I've used those protecting groups to control the one thing on leucine that can be reactive and the one thing on alanine that can be reactive, such that when I do the reaction, the coupling reaction with DCC, this is a reaction that forms the amide bond. We'll call that a coupling reaction because it links these two things together. The only thing that can happen is that the carboxylic acid group of leucine that's free can get converted into a good leaving group, then be attacked by the nitrogen of alanine to give a tetrahedral intermediate, which collapses and the leaving group leaves, and that gives me the desired amide bond and not the isomer. Then at that stage, I can do my two deprotection reactions. The hydrogenolysis of the benzyl ester and the acid catalyzed Bach deprotection reaction, and that's going to unmask my desired dipeptide molecule. All right, so that's the strategy. It's clunky, but it works. We've described a reaction that's multiple steps long. I didn't show you we had to start with leucine, make Bach leucine. We had to start with alanine, make Bach alanine. That's 2 reactions. Do the coupling reaction, that's 3. And then the 2 deprotection reactions, that's 4 and 5. So 5 total steps to get from just starting amino acids to dipeptide. Yeah?
Oh, we didn't do that gap. You're missing the methyl group on alanine, I think.
It's okay if you're that guy. I'm going to avoid insulting that guy. But if you really want to lean into being that guy, you need to go, actually. My kids use the nerd emoji and the pointing finger to be that guy, so yeah. Right, perfect. Thank you for that. Yeah, that's alanine. So 5 steps to get to the desired dipeptide. Why do we do that? To avoid the mess that would happen otherwise, not only with the undesired dipeptide, but also with what I was talking about earlier with the potential for multiple amino acids to couple on. Okay, so we'll say more about that next time. We're also going to talk a lot about the properties of peptides and proteins. I'll also introduce something that's called solid phase peptide synthesis, which is an even better way to do what we just described. All right, good luck on the exam. Happy Memorial Day weekend. I'll see you Wednesday.